this video, we're going to learn how to start doing some calculations with K. So our first calculation is going to be looking at how you might evaluate K. So how do you go about determining, since these K's are pretty important things, how do we go about determining or measuring what a K would be for a particular reaction? So we already know how K is defined, and so this is just a reminder. So this is for a general reaction, little a moles of A, reacting with little b moles of B, in equilibrium with C moles of C and D moles of D. So the lowercase letters represent whatever stoichiometric coefficients you need to balance this reaction, and the capital letters are standing in the place of formulas for different substances. And so this is how Kc is defined, products over reactants. So if we wanted to determine the value of Kc for some reaction, what we would do is design an experiment where we've got a reaction, we go into the lab, we let it come to equilibrium, and then we go in and we measure the equilibrium concentration of C, D, A, and B. And then you just plug them into this equation, and boom, you get a number. So that's a great idea if it's easy to do that. Now it turns out that for many reactions it might be hard to measure all of the reactants and products at equilibrium. It could be that some of those are just hard to measure analytically, or it could be that sometimes you end up with really small concentrations of reactants if the reaction goes mostly to completion. Then it might be hard to measure those guys because there's so little of them around. But as it turns out, you don't need to do that. We just have to be clever about it, and we can get by with just measuring one concentration at equilibrium. But then we have to do some fancier calculations. And so this is a way of me introducing to you how we do some of those fancier calculations. So let's move on now to our problem. So here's our problem. We're going to measure the equilibrium constant of a particular reaction. So the reaction that we're going to measure is this one. So we've got H2 gas reacting with I2 gas, and I'm going to leave off the phase labels, so I'm telling you that they're gases. And we're going to let that react and come to equilibrium with hydrogen iodide gas. So we make 2 moles of HI gas in the process of this reaction. And so we want to measure the equilibrium constant Kc for this reaction. So as I said before, one option is to let this reaction come to equilibrium, have an equilibrium mixture, measure the equilibrium concentrations of H2 and I2 and HI, and plug them all into the equilibrium constant expression. But for various reasons that might be hard. So let's say that we have a good analytical technique that lets us measure concentrations of HI very easily, but maybe it's hard to measure these two concentrations. So here's the way we're going to set up a problem. So initially, H2, so you do have to be clever. You have to know what your initial concentrations are. So we can get by with measuring just one equilibrium concentration if we know what our initial concentrations are. So initially we're going to take H2 at a concentration of 1 times 10 to the minus 3 molar, and we're going to mix that with I2 at a concentration of 2 times 10 to the negative 3 molar. We're going to allow those to react and come to equilibrium. So we've got no products initially, so they're going to react and come to equilibrium. So at equilibrium, the concentration of HI is 1.87 times 10 to the minus 3 molar. What is the value of Kc? That's what we're trying to calculate. So let's work this problem out. So we're going to work this problem out by using something called an ICE table. And I see I'm going to have to create some more space here, so let me do that. So we're going to use a little mathematical tool, and it's called an ICE table. So what you're going to do is first write your balanced chemical equation, and these are going to be like the column headings of a table. So we also need some row labels, and we're going to label our rows ICE, I for initial, C for change, and E for equilibrium. So that's a nice way to remember that. This is called an ICE table because of that. So what we're going to do now is fill in our ICE table. So chemical reactions are always written in terms of numbers of moles, right? So our table needs to be in terms of numbers of moles. But we don't have to just use numbers of moles. We can use anything that is directly proportional to number of moles. So if, for example, our volume stays constant, we can use molarity instead of moles. As another option, we could use partial pressure, because partial pressure is proportional to number of moles as long as our volume and temperature don't change. So we're going to use molarity because that's what we're given in our problems. So what do we know initially? So we know initially our H2 concentration is 1 times 10 to the negative third molar, and our I2 concentration is 2 times 10 to the negative third molar. So we've entered these as entries underneath these column headings for H2 and I2, and those are our initial values. Now also we know what our initial HI concentration is. Well, we didn't have any, so that initial concentration is 0 molar, 0 moles per liter. Okay, now change, we're going to leave these little spaces empty right now because we don't know what the change is. But we do know one other value. We know the HI concentration at equilibrium. So we're going to go find that underneath the HI column and the E row. We're going to enter our equilibrium concentration. So that's going to be 1.87 times 10 to the negative 3 molar. Very good. So now we just need to figure out what these empty spaces are. So our goal is to figure out what all the equilibrium concentrations are, and then we can substitute those into the equilibrium constant expression. So we started off with 0, we ended up with 1.87. Oh, so it's easy to figure out what our change is. We gained, so I'm going to put a little plus sign here, 1.87 times 10 to the negative 3 moles per liter. So we can just do the math down the column. 0 plus this number equals this number. So it's just a math. 0 plus 1.87 times 10 to the minus 3 equals 1.87 times 10 to the minus 3. Okay, now we know how much the HI changed. So now we can use the stoichiometry to figure out how the H2 and the I2 changed. So we know from this reaction that for every 2 moles of HI that we make, we lose 1 mole of I2 and 1 mole of H2. In other words, for as much HI as we gain, we're going to lose half as much of that I2. So you can just use your stoichiometry. So it says that this number, the change in I2, it's going to be half as much as the HI because we make twice as much HI as we lose I2. So what we need to do is divide 1.87 times 10 to the minus 3 by 2. And that number is 0.935 times 10 to the negative third. Okay, so why did I put a minus sign up here? Because, if you divide this by 2, you don't get a negative sign. But the negative sign is reminding me that this is how many moles of I2 we are losing. The reaction is going to go in this direction. Why? Well, it has to make some product to get to equilibrium. So it's going to make some product. And so now we know how much I2 we're going to lose. We're going to lose, hence the negative sign, 0.935. And we're going to lose exactly the same amount of H2. So I'm going to write a minus 0.935 times 10 to the negative third. So it's gotten a little bit crowded here. I should have made my table a little bit bigger. So now we are ready to sort of do the math down this column. So we take H2, which was initially 1.1 times 10 to the negative third, and we're going to subtract from that 0.935 times 10 to the negative third moles per liter, because that's how much we lose. And so that gives us an equilibrium concentration of 0.065 times 10 to the negative third molar. And then now we do the same thing for the I2. So we have 2 times 10 to the negative third molar minus 0.935 times 10 to the negative third molar. And that gives us a value of 1.65 times 10 to the negative third molar. So now we have all of our 3 equilibrium concentrations. And we've used the ICE table to help us figure those out. Now we're ready to do the next step, which is where we substitute these into the equilibrium constant expression. So Kc for this reaction is products over reactants. So that's Hi squared divided by the concentration of H2 and also divided by the concentration of I2. So there's our equilibrium constant expression. So these are equilibrium concentrations. So that's the E row of our ICE table. So now we're just going to go in and plug in these numbers into this expression. So our equilibrium Hi concentration is 1.87 times 10 to the negative third moles per liter, and that's going to get squared. Now I'm not going to put in my units because we remember that equilibrium constants are unitless numbers. So then we're going to divide by the H2 concentration and the I2 concentration. And we just punch this carefully into our calculator, and when you're done, and you should check this to make sure that you get the same result, you'll get 51 about. So to two significant figures, we've got 51 as the value of our Kc for this reaction at this particular temperature, which they didn't tell us in the problem, but it was some temperature. And so that's how we can use a clever measurement of initial concentrations and one equilibrium concentration, and using this clever tool called an ice table to calculate our Kc. Now you should get comfortable using ice tables because we're going to be doing that a lot when we solve equilibrium constant problems.